Good morning, everyone. This is our next module, which is known as mathematical modeling of the system. So, what is mathematical modeling and why is so important for quantum system engineering? As in the previous lecture, so in the introductory part of the lecture, I have discussed this mathematical modeling part. Because this quantum system is a purely mathematical paper, and once you have to design the system, definitely you must have to go through a part which is known as the mathematical modeling. And once you can design or model the system mathematically in such a way so that this can give you the more accurate result. More accurate result means it gives some desired value of the output corresponding to the changes input, corresponding to changing different kinds of input. So whenever we model the system, we will model the input also. So actually modeling means, mathematical modeling means normally description of the system in by using some mathematical term. Better we can call it differential equation. By some differential equation we will describe any system, right? So once you describe the system in terms of differential equation, definitely based upon the differential equation we will apply different kinds of input to the system and get the output. So before going to discuss in detail about the mathematical modeling of the system, first of all two or three more terms I would like to say, that is Laplace transform. What is this? This is very known term, and throughout your courses this is a very powerful mathematical tool which is used to describe any system. And what is the function of the Laplace transform? Say for example, any system is described by, say for example, d2y dt2 plus a dy dt plus y is equal to x. Actually what happens, this is your input and this y is your output. Normally in mathematical modeling we describe the system input output relationship. So if the relationship of the input output is described by mathematical equation, that is the mathematical modeling of the system. And normally the variable y is used to denote the output and variable x is used to denote the actually input. So what is this? This is a differential equation. This is a second order differential equation. Clearly you can see it. And what is the role of the Laplace transform? Role of the Laplace transform is that algebraic manipulation of the equation. That means easily we can solve, or you can get the system in mathematical domain in such a way such that the algebraic manipulation will be much more easier. So what you have to do, you have to get the Laplace transform on both sides. So what we get? We get s square ys plus s a ys plus ys is equal to x of s, right? So once you are getting the Laplace transform of any differential equation, definitely all the variables will be the function of s. That is the Laplace. If ft is your function in time domain, see this is a function of t, so this is a time domain function. So once we get the Laplace transform, you will get f of s. Normally this f is expressed in capital and this time domain to frequency domain or Laplace domain. This is shifted s. So this is a function of s, and you see here, as this is a second order term d2y dt square. So if you actually Laplace transform of this term s square ys, this s square into ys plus or minus some y0 element will be there, right? So that is the actually details about the Laplace transform. I am not going to discuss about it in whatever that part of the Laplace transform is required in my study or in my lecture, that I am focusing on. So even neglecting that initial part, here there is no y0, x0, this, there is no like this. That means the initial value of the output as well as the initial value of the input, right? So output yt. Initial value means at t is equal to 0, the value of yt is equal to y0. Similarly, x0 means the value of xt at t is equal to 0. This is your x0. So these are the two initial conditions, that means initial values of the output and input. These values are taken as 0. So what we'll get? We will get ys by xs. From this mathematical representation, just we can say, you can write it like ys by xs, 1 by say s square plus as plus 1, right? Just s square as plus 1 multiplied by y is equal to xs. So ys by xs will give you this is. So what we will getting, that is the Laplace transform of output variable divided by the Laplace transform of input variable, right? So output variable by input variable both are Laplace transform, and one more important thing is that here we are considering the initial conditions is equal to 0. Initial condition is equal to 0. That is very much important. So once the initial condition is taken as 0, so this ys by xs is known as the system gain, right? So what is this? This ys by xs is known as the system gain. Okay, so system gain. System gain means output by input. Here we are writing in terms of Laplace domain xs, where initial condition is equal to 0, that is s square plus as plus 1. So this is your system gain, right? So if this is your system gain, so this is termed as g of s. This is the gain and this is a Laplace variable. This is your gain. So mathematically, what we can say, if this is xs, say this is ys, this is a basically series path, right? What happens? This input passes through this block. This is your system. So you can write it as gs. This is your plant, right? We can say it as system or plant. Already we have discussed the terminology. Now this is your xs, this is gs and ys. And from this relationship, what you see? This xs is multiplied to gs to give you ys, right? So xs, gs, ys. That means ys by xs is equal to gs. And this gs is known as transfer function. So what is the basic definition of the transfer function we learned from here in regard to control system? Basic definition of the transfer function means like this. Say any system which is described in continuous domain by some differential equation, and if you get the Laplace transform on both sides, you get all the variables to be transferred in the Laplace domain, and then the output Laplace transform of the output variable divided by the Laplace transform of the input variable when the initial conditions is 0. That is known as the transfer function. That is nothing but the gain of the system. Or you can put here, instead of gs, you can put it 1 by s square plus s plus 1, right? So here we can put like 1 by s square plus s plus 1. Now once you get this kind of transfer function, so definitely there are two more terms coming. What is? First of all, that is order of system. Second one, type of system, right? So order of that system and type of the system, these are the very important terms, because once you go on designing any system, then these will be the term which will be frequently coming, and we will discuss them in terms of the type of the system or order of the system. Now if the transfer function is like this or gain of the system is like this, then what is the order and what is the type of the system, that I'm discussing in this lecture only, right? So this is our system. This is your input, this is your output, this is your system. What is this? So we write this gs, that is the transfer function of the system, that is 1 by s square plus s plus 1, right? So there are two terms. one numerator, one denominator. So numerator, that is a function of s, and denominator also, that is a function of s, right? So what is the numerator you are getting here? Nothing. So numerator is 1 irrespective of s, that is constant 1. And what is the denominator? That is s square plus as plus 1. So from the denominator, if you make the denominator is equal to 0, say if you make the denominator is equal to 0, what will get? You get a square plus as plus 1 is equal to 0. That means this is a second order factor. So if you solve this, you will get the two poles, s1 and s2, right? How can you get it? By using the Sridhar-Acharya. So s is equal to minus of b, here minus of a plus minus root over b square minus 4ac, 4 into a coefficient 1 into 1 by 2 into a. A is the coefficient of s square, right? So you get minus a plus root over a square minus 4 by 2, and this is s1, and this is your s2 minus a minus root over a square minus 4 by 2. So two roots. What will get? Two roots, because this is known as the roots. How can you get the roots of the transfer function? If you make denominator is equal to 0, you get the roots, and these are also known as poles of the transfer function or poles of the system. Similarly, if there is any term in the numerator, by using the same procedure, you can get number of numerator equal to 0 and get the defined values of s. So this s, what is this s? S means some complex quantity, right? S means some complex quantity. Complex quantity, how this kind of complex quantity is framed in a control system domain, that uh, I will discuss here. So similar to the coordinate system, we know this s. S is equal to plus minus real plus minus j imaginary. This is a complex variable. You know about the complex variable. It is having real part, one is imaginary part. Now, Leibniz just have framed the system like all the real values are along this horizontal axis, all the imaginary values are along the imaginary axis. This is real axis, this is imaginary axis, right? So, for example, s is equal to minus 2 plus j4. So real part is minus 2, imaginary part is plus 4. So real part is minus 2 means this is say minus 1, this is your origin 0, 0. Minus 1, minus 2, this is your real value, and plus j4. That means you have to move along the imaginary axis by 4 amount here. So what is the location of this pole? This I can say as pole. Pole means denominator of the transfer function. So or 0. So this is the positions of the pole. So whatever or whenever we are calling say minus a plus minus root over a square plus 4 or minus 4 by 2, that means there are two locations of the force, right? One is either here, either here, either here, or either here. This is known as S-plane, right? So these are the actually definitions, or these are the mathematical background you should know before going to discuss about the quantum system in details. So S means some frequency domain, and that is having some plane. That plane is having two coordinate system. One one is like xy coordinate system. This is real axis and this is imaginary axis, and all the values you will get either poles or in zeros. What is the zeros? If you get numerator of the system equal to 0 and get the value of s, we get this as known as the 0. Similar, if the denominator is taking as 0 and solution of the denominator you will get, and that value of s will give you the poles. So these are the concept of poles and zeros. Now what I was discussing here about the order of the system. So order means, say for example, GS equal to, I say, and write s square plus 4s plus 8 like this. So order means the number of poles of the system. In terms of control system, I can say it. Number of poles of the system. So how can you get the number of poles of the system? A system is described by this, right? What is this? G is equal to 1 by s square plus 4s plus 8. Now 1 plus 1 by s square plus 4s plus 8. If we solve it, s square plus 4s plus 8 equal to 0. This gives you s1 and s2. That means this is a second order system. Second order system, because we are getting 2 poles here. So if you get the 2 poles, that means this is a second order system. If the system is having 3 poles, the order of the system must be third order. So this may be s cube plus dot 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 something. Or we can get the example like gs is equal to 1 by s cube plus 4s square plus 7s plus 9. See, if you solve this, this is a third order solution equation. So you get the value of s 3 poles. That means this is a third order system. Okay, so this is the concept of order. Now what is the concept of type? Once you know the order, then type of the system is very easy to find out. See, a system you can write is like 1 by s into s square plus 4s plus 5. First of all, what is the type of the system? Let's see, type of the system. So in order to get the type of the system, type of the system means number of poles at s is equal to 0 or origin. S is equal to 0 means from the s-plane graph. Already I have discussed, this is your real, this is your imaginary, right? So this is your origin. S is equal to 0. So if there is a pole, there is a single pole at one pole at s is equal to 0, indicates this is a type 1 system. 2 poles at s is equal to 0 means this is a type 2 system, and so on, right? So what is this about? Here you see, in order to get the poles, first of all what you have to do, you have to just get the denominator. So s into s square plus 4s plus 5 equal to 0, right? Here if you solve, what will get? S is equal to 0 and s square plus 4s plus 5 equal to 0. Definitely from this solution you will get the two values of s here and another value is there. So that means altogether what you will getting? 3 number of poles altogether. That means 2 poles will be coming from this factor, 1 pole is coming from this factor. So 3 poles altogether. So this is a third order system. Now what are the number of poles at the origin? 1, right? 1 pole at the origin. So this is a basically type 1 third order system, right?